In the pre-lecture, we introduced the idea of concept learning, which is a supervised learning algorithm that attempts to find the target function. We looked at it in the setting of a binary classification problem of enjoying a drink. And we saw that here, in this particular problem, we have discrete attributes for the input values, right? So we had inputs 1 through 6, and they all took discrete attribute values. We were supposed to learn a target concept of whether somebody enjoys the drink or not. We also learned a specific algorithm for doing it called FindS as part of the last parts of the pre-lecture. It returns a maximally specific hypothesis that's consistent with the data set that's been exposed to it. Although it's one solution to the problem, it's not a particularly great one because it returns one of the maximally specific hypotheses that's consistent with the data set. But there could be several or many, depending on the problem and the ordering of the data that's been exposed to it. We would actually like to have an algorithm that returns the entire set of hypotheses within the hypothesis space that's still consistent with the data set. And we're going to learn that now through the candidate elimination algorithm in this post-lecture part. However, to get to that understanding of the candidate elimination algorithm, it helps to understand the idea of version spaces, which is what the candidate elimination algorithm is based on. So what exactly is a version space? We're going to say a version space is specific to two variables, a hypothesis space, which is denoted as all the hypotheses that are possible for a particular learner. Okay, so here in this part of the lecture, just like in the pre-lecture, we are talking about the conjunctive learning algorithm. It's also specific to the data set that has been exposed to the learner. So the version space is basically the subset of all of the hypotheses that are consistent with the data set. Okay, so as we talked about with the FindS algorithm just picks one particular hypothesis that's maximally consistent, maximally specific and consistent with D, but there could be more than one. Using the version space, we hope to represent all of the hypotheses that are consistent. Now, if you understand this, if we are given a large enough data set with lots of telling examples, we might be able to actually locate the target function and reduce the set of all of the hypotheses that are consistent to actually the target concept that we want to find, provided that the target concept is actually in the hypothesis space. So this gets back to our other point earlier, where we were saying that the conjunctive learning algorithm only can recover conjunctive hypothesis. So if the hypothesis doesn't match the target function, let's say the target function is disjunctive, then we're out of luck. But oftentimes we won't have enough data points to locate the concept exactly. Sometimes it'll be insufficient, actually most of the time. Then we can say the version space's size represents the amount of uncertainty on what the target concept actually is. So with this definition, we can see that the version space actually contains all the consistent hypotheses, including ones found by FindS. You might be thinking, well, there's another way to do it. We could use this very simple algorithm of making a list and checking it twice. Well, if we have all of the hypotheses as a hypothesis space, like a script H, what we could is just list out all of the particular hypotheses that are available. Then when we're exposed to training examples, we're just going to eliminate ones that aren't consistent, right? So if we see a negative example, and that negative example is supposed to be classified positively by a particular set of hypotheses, then all of those hypotheses are going to be crossed off, right? So that's exactly what this list then eliminate algorithm does, right? It first sets the version space that we want to find, as all of the hypotheses that are possible within H, okay? And we're going to remove, for each training example, any hypothesis where our hypothesis predicts a result that's not consistent with our target function, right? Once we've run this loop all m times for all of the m instances in our data set, okay? That means 1 through m here, okay? Then we're going to output the list of hypotheses in the version space. So, will this work? Definitely. It'll work just fine. We will end up returning all of the hypotheses that are consistent. However, unfortunately, this is really totally unrealistic. As we saw, it requires a full search of the hypothesis space. As we saw in the previous part in the pre-lecture, even for a simplified version of our target problem, where we would have only 6 binary attributes, that means we would have 2 to the 6 different possible instances, data items, and then we would have 2 to the 6 concepts, right? So all of these would be the size of the hypothesis set, right? So this is too large a number to enumerate all the hypotheses for even this very small finite sized H. So here's a version space illustration for the enjoy drink problem after we have observed the 4 training examples as we saw in the pre-lecture. Go ahead and take a look at the pre-lecture slide 9, where we showed you 4 training examples. Basically, after going through those 4 examples, we saw that there were drinks that were coffee with evaporated milk and iced being the most specific concepts, and some other concepts that are most general. It could be any type of drink that is a coffee drink and any type that had evaporated milk. And then between these 2 concepts of the most specific and the most general, we can see we have other ones that are possible. We could, for example, combine the specific hypothesis with the general one in this direction, okay? Where we take the coffee from here and the ice from there to get this hypothesis. Or for example, we could take the condensed evaporated milk from this one and the ice from this one and end up over here, okay? From the other 2 combinations, we get the same intermediate hypothesis. So all 6 of these different ones, okay, 1, 2, 3, 4, 5, and 6 hypotheses. These are all the hypotheses that are consistent after observing those 4 training examples. So our candidate elimination algorithm is actually going to do the same thing as the list then eliminate algorithm. It's going to go through the version space and cancel out hypotheses that are inconsistent, but it's going to do so in a way that's much more compactly representing of the version space. We're going to utilize the same hypothesis is more general or equal to operator that we introduced in the pre-lecture. We can intuitively think of the version space as having 2 boundaries, a general boundary where that describes the set of maximally general members of the hypothesis space that's consistent with the data set. In other words, there isn't any other hypothesis G prime that's still in our hypothesis set, okay, that is still consistent with the data set and is more general than the ones that are any one of the members of the G set, the capital G set, okay? And similarly for the specific boundary. For the specific boundary S, is going to be the set of maximally specific members of the hypothesis set that's consistent with the data set in such a way, again, that there is no other hypothesis S prime that's going to be more specific than any member of the set S, okay, where S here is the capital S, right? So any member of the set is going to be small s, okay, in such a way that all of these are consistent with the data set, okay? So just like we saw in the previous picture here, right, we can think of the specific set and over here and the general set down here as being the bounding box for all of the members of the hypothesis space that are consistent with the data set. So this is our version space of H of D. So every member of the version space that's valid, right, meaning it's consistent with the data set, is going to have to lie between these two boundaries, okay? And so we can compactly represent it like this. We can say that these two things are equivalent to say that if we have a version space, that means all of the hypotheses that are in the version space must be in the possible set of hypotheses admissible by the learner and obey this particular formalism. This will be our right-hand side that we're going to use for the next part. Okay, basically, any hypothesis must be between the two extremes of being a general hypothesis and a specific one. And so the proof of the version space representation algorithm can be done in two parts. Okay, we first, as part of this thing over here, have to show that the version space is the same as saying that within this version space, there has to have a hypothesis that is within the hypothesis set that satisfies the right-hand side. Okay, so every H that satisfies the right-hand side is actually inside our version space. That's the first part of the proof. And the second part of the proof, which we're not going to cover, but you can follow the instructions over here, is to show that every member of the version space actually satisfies the right-hand side. Okay, so let's get started on this first part of A, all right? What we want to do is use the right-hand side definition, right? Because it says if it satisfies the right-hand side, we want to show that it is part of the version space. So we're going to choose an arbitrary member of G, a member of S, a member of H, such that the right-hand side is actually obeyed. Okay, that means in this case that the H is somewhere between the G and the S in terms of specificity. So every positive example that is inside of our data set is going to satisfy S by the definition of what a specific hypothesis is, okay? And because our S value, right, whatever we put here, is going to be a specific hypothesis, we know it's going to be either equal to or less general, more specific than the H that we've chosen, okay? Because of this, we know that the satisfaction also holds for H. Remember, satisfaction just means that it gets a positive outcome, okay? So this is the case for positive instances that we want to look at, all right? For negative instances, we're going to say that every negative instance does not satisfy our general hypothesis by the definition of what a general hypothesis is, right? Because if it's going to be rejected by the general hypothesis, it's not going to be a positive instance, and then there'll be a negative instance, okay? And because of our construction, our general hypothesis must be more general than our normal hypothesis that we're looking to try to find. That means this one here, okay? Then every negative example is also not going to satisfy the hypothesis that we're looking at, right? So with these two parts, then we know that actually we're satisfying something a bit stronger than satisfaction, right? It is consistent, right? Because it must be a positive example if the target concept classified it as positive, okay, and H will also classify it negative if it is a negative training instance, which means that the target concept also classifies it as negative, okay? So if it's consistent with our data set, then it must be in our version space. We've just proven this.